Okay, calculus students, in this problem we're going to consider continuity of a function, and here we have a piecewise function. It's a rational function when x is not equal to a number, and it's a constant or some value when x is equal to a number. Now I didn't fill that number in because the thing I want you to consider is you could almost tell what the problem is going to be just by looking at the function. So you can see that x cannot be equal to minus 3. So you could almost fill that in on your own without it even being told to you. And then here x will be, when it's equal to minus 3, you want to fill some hole in. If you try minus 3, you see obviously you get 0 in the denominator. But if you check the numerator, you'll see that you get minus 3 squared is 9, plus minus 3 is 6, 6 minus 6, so you get 0 over 0. So the function clearly isn't defined at minus 3, x equals minus 3. Moreover, if you were to take the limit as x approaches minus 3, you'd see that your result would be inconclusive, right? That's an indeterminate form. Now, before we consider continuity, I just want to remind you of the definition of continuity. And that is that the limit as x approaches a of f of x is equal to f of a. So you need to be able to put in the a for that f, all right? However, continuity is really, you can think of it as a triangle. Has these three legs. And for this statement to make sense, really this left-hand side has to make sense. That means that this limit has to exist. And for that limit to exist, you need the left-hand limit to equal the right-hand limit. So that has to hold. And then on the right-hand side, you need this value of the function to be defined. And then recall that even if the function is defined and the limit exists, it doesn't necessarily have to be the case that they're equal to each other. So to conclude the continuity triangle here, you need the limit of f of x as x approaches a, so the limit exists, to actually equal f of a, if f of a is defined. All right, so we've seen examples of that, especially when there was a hole in the function, right, where f of a could be defined if it was not filled in the proper place. Okay, so enough of that. Let's use that definition of continuity here. So the thing we need to find here is we want to show that we want to choose a value for k so that f of x is continuous. So if we plug in minus 3, so when x is minus 3, it's equal to k. Now for this to be continuous everywhere, we want the limit as x approaches minus 3 to be equal to f of minus 3. So this is what we want to show. Okay. In other words, and f of minus 3 is equal to k. So we want k to equal this limit. Now we need this limit to exist, so we need the limit as x is approaching minus 3 from the left to equal the limit as x approaching minus 3 from the right. Now x is not equal to minus 3, so for this part of the function, for this condition, for this piece of the function, so that means when x is less than minus 3 and when x is greater than minus 3. So f of x from the left of minus 3 and from the right of minus 3 is this piece. So we don't have much of a choice here when we're considering the limit. So we're just going to, the limit from the left or the limit from the right. So we're just going to compute the limit as x approaches minus 3 from both sides of minus 3, because that's this piece. So I will write that down. X squared plus x minus 6 over x plus 3. All right, now, since we know that that's 0 over 0, that's inconclusive, okay, because that's an indeterminate form. So I'm going to see if I can simplify the top, and it turns out that I can. It does factor. Like that. Because I'm taking a limit, I can cancel those out. And now I can evaluate this limit. That's just a polynomial. So I get minus 5. So the limit as x approaches 3 from both sides is minus 5. So I can finish this off, and I have minus 5 is this limit. But that has to equal k if this condition is going to hold. So I should choose k equals minus 5. Then my function will be continuous over the whole real line. All right, good luck.